A shelter will only be effective if the building in which it is located remains standing. It is unreasonable to design a shelter within a building with the expectation that the surrounding structure may collapse. Although the shelter must be able to resist debris impact, it is not reasonable for it to withstand the weight of the building crashing down upon it. Therefore, the effectiveness of the shelter will depend on the ability of the building to sustain damage but remain standing. The ability of a building to withstand an explosive event and remain standing depends on the characteristics of the structure. Some of these characteristics include mass. Lightweight construction may be unsuitable for providing resistance to blast loading. Inertial resistance may be required in addition to the strength and ductility of the system. Shear capacity. Shear is a brittle mode of failure, and primary members and/or their connections should therefore be designed to prevent shear failure prior to the development of the flexural capacity. Capacity for resisting load reversals. In response to sizable blast loads, structural elements may undergo multiple cycles of large deformation. Similarly, some structural elements may be subjected to uplift pressures, which oppose conventional gravity load design. The effects of rebound and uplift, therefore, require blast-resistant members to be designed for significant load reversals. Depending on the cable profile, pre-tensioned or post-tensioned construction may provide limited capacity for abnormal loading patterns and load reversals. Draped tendon systems designed for gravity loads may be problematic. However, the higher quality fabrication and material properties typical for precast construction may provide enhanced performance of precast elements designed and detailed to resist uplift and rebound effects resulting from blast loading. Seated connection systems for steel and precast concrete systems must also be designed and detailed to accommodate uplift forces and rebound resulting from blast loads. The use of headed studs is recommended for affixing concrete fill over steel deck to beams for uplift resistance. Redundancy. Multiple alternative load paths in the vertical load carrying system allow gravity loads to redistribute in the event of failure of structural elements. Ties. An integrated system of ties in perpendicular directions along the principal lines of structural framing can serve to redistribute loads during catastrophic events. Ductility. Structural members and their connections may have to maintain their strength while undergoing large deformations in response to blast loading. The ability of a member to develop inelastic deformations allows it to dissipate considerable amounts of blast energy. The ratio of a member's maximum inelastic deformation to a member's elastic limit is a measure of its ductility. Special detailing is required to enable buildings to develop large inelastic deformations. Historically, cast-in-place reinforced concrete was the preferred material for explosion mitigating construction. This is the material used for military bunkers, and the military has performed extensive research and testing of its performance. Among its benefits, reinforced concrete has significant mass, which improves its inertial resistance. It can be readily proportioned for ductile behavior and may be detailed to achieve continuity between members. Finally, concrete columns are less susceptible to global buckling in the event of the loss of a floor system. However, steel may be similarly detailed to take advantage of its inherent ductility, and connections may be designed to provide continuity between members. Similarly, panelized precast concrete systems can be detailed to permit significant deformations in response to explosive loading, as demonstrated by the performance of Cobar towers. Protective design further requires the system to accept localized failure without precipitating a collapse of a greater extent of the structure. By allowing the building to bridge over failed components, building robustness is greatly improved, and the unintended consequences of extreme events may be mitigated. However, it may not be possible for existing construction to be retrofitted to limit the extent of collapse to one floor on either side of a failed column. If the members are retrofitted to develop catenary behavior, The adjoining bays must be upgraded to resist the large lateral forces associated with this mode of response. This may require more extensive retrofit than is either feasible or desirable. In such a situation, it may be desirable to isolate the collapse region rather than risk propagating the collapse to adjoining bays. The retrofit of existing buildings to protect against a potential progressive collapse resulting from extreme loading may therefore best be achieved through the localized hardening of vulnerable columns. These columns need only be upgraded to a level of resistance that balances the capacities of all adjacent structural elements. At greater blast intensities, the resulting damage would be extensive and create global collapse rather than progressive collapse. Attempts to upgrade the building to conform to the alternate path approach would be invasive and potentially counterproductive.